Right, yep, so recursion and then sorting is our initial start for tonight. Hopefully get through all that. Include the subtitles. Yes. See where that is. Live transcript. Live transcripting is on. Is that popping up? Okay. Okay, so recursion. Let's see what we got here. All right. What number are we at here? So section 2. Recursion. All right, so this is the beginning of test 2 area. And recursion is just a function. Calls itself. All right, so this is hopefully a review for everyone, but just gotta make sure. There's some components. We have a base case. This is what causes recursive calls to stop being made. A production rule. Something that changes the state between function calls. It causes us to approach base case and then the recursive call itself. The function calling itself, which may be indirectly. All right, so summation series, which shouldn't be recursive. It is a simple one to go with. All right, so our function is called summation, returns an int, and we just return n back plus summation of the next smaller value of n, that is. So if we were to go ahead and do a stack trace here and look at various states, right? We got main, and then say main calls just as a cout summation of 5. All right, so we'll have several calls to summation. And here n will be assigned the value 5. And it's going to return back 5 plus summation of n minus 1, which is before. And we'll have several rounds of this. Summation 4, which is going to be 4 plus summation of n minus 1, which is just 3. And I'll rinse and repeat a few times until we eventually get to our base case. Which this example is just going to be 1. Not 1 rather, 0. And 0 just becomes 0. All right, so we hit our base case. This function returns 0, so we had 1 plus 0 back. That gets sent back to the caller, which is just 1, 2 plus 1, which is 3, 3 plus 3 is 6, and then 4 plus 6 is 10, until we get back to 5, sending 11 back to main. All right, so this is a trivial example. It could be replaced by a loop, or better yet, a formula n times n plus 1, which is divided by 2, right, which in this case n5 times 6 divided by 2, which is 15. I think I said 16 earlier because I was doing some bad math. That's 15. All right, this is a linear problem. We run into nonlinear problems, and recursion is going to help solve various problems in a much simpler way. And trying to use a non-recursive pattern. All right, so there's a version of quicksort or merge sort, as we see those that are going to be using the recursive patterns, but see those when we get there. Questions about recursion? Okay. The amount of memory recursion takes depends on many stack frames it's going to create. All right, so the stack frame requires memory allocation for the parameters and local variables. It's going to require memory for the return address and the return value. The stack frames aren't usually particularly large. Bytes would be the correct unit of measure. All right, assuming a 32-bit system, 4-byte return address, 4-byte return value, assuming there's a return value. And the Wolfwigo summation that we had right here is just a 4-byte argument. So probably a little bit other overhead, but 12 bytes per stack frame. So it's not going to take a whole lot. Okay, so sorting data, which is to mean placing order based upon the data points of a set of data. Typically stored in an array, and we'll presume the sort is in an ascending order unless otherwise specified. Sorts are generally going to range from a big O of n log n to a big O of n times n, or aka n squared. In this section, we'll cover bubble sort. Selection sort, insertion sort, quick sort, and merge sort. So bubble sort is our somewhat trivial one, mostly for educational purposes because its algorithm is quite straightforward. So our algorithm is just repeatedly compare adjacent elements. If those elements are out of position, swap them. And we'll repeat until sorted. Okay. Go ahead and just drop in some pseudo-random data. We can sort it. All right, so we'll sort 7 values. First value will be 15. And we'll get a 6 in there. 18 to 9, 11, and 4. All right, so there's our initial state. And actually, let's add a state column. All right. So our state 1. We are going to go ahead and compare these two values to see if they are out of order. If the two values are out of order, we'll go ahead and swap. All right, so let's go ahead and add some key here to our colors. Orange is compare, and green is swapped. And then we'll keep repeating the process. Comparing the next two elements. And if they're out of order, we'll go ahead and swap. Since 15 is in its relative position to 18, no swapping needed to be done. All right, so let's go ahead and leave that record alone. And then we'll move along to comparing next two data points, and then we'll rinse and repeat. Oops, wrong one. All right, 2 and 18 are out of position. So we're going to go ahead and perform a swap on those two data points. Colors out of sorts here. Let's get that fixed. Okay. All right, 2 and 18 were compared and found to be out of position. So we swap them into sort position relative to each other. But we still have ways to go here. To get things where we want them to be. All right, state 8, 9 and 18 swap. And we keep on carrying along here. After making our first pass across this data, we'll ultimately have 18 into its final sorted position. All right, so 11 and 18 are being compared next. Those are out of position. 18 is going to go ahead and keep on bubbling up until it finds its way to its sorted spot in the array. So we've got one more round here to do on our first loop through the data. All right, 18 and 4. And we'll see that those are out of position. So we will do our last swap on the first pass. Giving 18 its final place in the result set. And we'll go ahead and mark that as, let's see, purple work. It's a little hard to read. Teal it is. All right, one more color here. Teal is final sorted position. And then we'll start back over. Go back to the beginning of the array. And we'll go ahead and compare. First two elements, but this time we'll only need to go up to 4. And repeat. Repeat. Until we get into our final. So we'll go ahead. The set just got a little bit smaller. 6 down to 4. 15 will get pushed up to its final sorted position. And we'll repeat the above again. All right, let me add a state in here. So I can see the data. All right, so we had 6 stay where it was, 2 moved over, 9 moved over, 11, 4, and 15. And we got 15 into its final position there. All right, I guess I'll put the repeat here. And add the state. Be easier to read after the fact, I guess. Always feel free to ask a question, throw a question at me if something isn't making sense. Okay. All right, so we had 15 slide over. And now 6 and 2 will compare. All right, 6 and 9 compare. Just clear all those colorings. They're good until we get to 4 and 11, putting 11 into its final sort of position. And we continue on 2, 6, then 4 and 9, 9 in its final sort of position. Each of these is taking an entire pass on a subset of the array. 4 and 6 get us to our final sort of position. We're actually sorted here at this point, but we don't know that we're actually sorted yet. So we will have to do one more. We see 2 and 4. 2 and 4 is already in proper position. No swap was needed. We can go ahead and stop the sort there. All right, so we iterate down the array, swapping adjacent elements as needed. Then we repeat that iteration till all n elements are in sorted position. So that's a linear step times a linear step, giving us big O, all right, n squared. Let's go ahead and dig the code up. Take a look at that. Go to our sorting section in files, pull down our sorts code file. Okay, all right, so this has 3 of our sorts: bubble, selection, and insertion. And a helper print function. Let's see, let's get that a little bigger. All right, bubble sort. All right, it's not taking anything, or rather it's not sending anything back. 2 arguments, the array and how big the array is. And then we're going to go ahead and do a pair of for loops, right, which gives us our n squared O notation. We got a few local variables that we're going to make use of here. All right, so our outer for loop goes to length minus 1. All right, so the outer for loop is continuing how deep into the array we're going to go, and then we're going to decrement I. So I is going to control how far down the array we need to swap our values to. This implementation of bubble sort does have a check flag so we can try to exit early. If the test gets set inside our if block, it means we did a swap. If we did a swap, then there's the potential for more work that still needs to be done to get the array into a sorted state. If the test never gets turned on, then we can break out of the loop. So for example, if we're given an already sorted array, and us sending sorted array to the sort, it'll make one pass through this code here. All right, for loop comes in, this inner loop runs one time. We never set the test flag, and then we'll break out of the loop because we've detected that the array is sorted. Assuming that's not the case, inner loop starts at 0 and only goes so far as I. Notice right, I goes 1 less than the length because we are going to have j go 1 greater than itself. So this +1 here is why we have the -1 up here, so that we stay in bounds of the array. And if we don't like the left-hand side value of j versus the right-hand side value, j +1, we'll go ahead and do a simple swap. All right, copy the one value into a temporary variable, replace that value with the other, and then replace that value with a temporary variable, and then set our test flag. And we'll just stay in this loop looking at our adjacent values until we get j to 1 less than the last element, in which case we compare n-1 and n, assuming 1-based indexing, our last 2 elements to say it more succinctly and see if they need to swap. That first pass across the array and from the inner loop gets us to 1 element into its sorted position. All right, I goes down 1 and j starts over at the beginning, just like we did on the whiteboard, and we rip on through. Any questions about bubble sort? Okay. Next up, selection sort. Okay. Our algorithm here. Grab. Okay, so we're going to be logically. Sorry, one second. Logically divide the array into two partitions. And empty sorted partition. And the rest of the array as the unsorted partition. We're going to repeatedly search the unsorted partition for the extreme value, right, minimum value being the default. And select that value and underline select, that's the name of the sort. Select that value. And append that to the sorted partition. Okay. All right, same basic idea. Okay, index and state. All right, and then we've got our data. All right, let's go ahead and use our same data. May as well. All right, so there's our initial state. Going to state 1, we will have selected 15 as our candidate smallest value. All right, so let's go ahead and initial smallest is green. And then let's just say our candidate smallest. Go ahead and switch that to orange. And then actual smallest. Go ahead and get another color for that. We'll get there in a second. All right, so we're going to be looking through 15 is our smallest. Then we're going to go ahead and toggle. Six being a better smallest value. Switch that to orange, go down our list, looking for someone smaller than 6. 18 is not smaller, 2 is. So go ahead and track that. 9 is not smaller, 11 and 4. None of these are smaller. Then 2, so 2 becomes the smallest value. So we're going to go ahead and take that and we'll swap the smallest value with the end of the sorted partition, right? So our sorted partition is empty. So index 0 will become our sorted position. Let's give that a light blue, and then teal has us in our sorted position. So 15 got swapped with 2. So go ahead and try to color those. Let's see, let's be consistent here. What colors? Green is swapped. Let me fix my color scheme here. Okay. And that's good. Initial smallest. Just add a color to the spectrum, shall we? Let's make it red. And actual smallest was that blue. And get to green swap. All right. Got our color palette squared away here. Helps if I click the right button though. So much easier with markers sometimes. It's a balance. Some things are easier. Some things are easier with the digital and some things are easier. Good old analog. Okay. So we now have 2 into its final sorted position, which is teal. Great. So much for. Okay, I do have it. All right. And then we'll repeat the process on the unsorted partition. All right, so we have 2 sorted and the unsorted partition that needs to be processed. So I'll go ahead and grab 6. Say you're the smallest value until I find someone smaller. Look at 18, not improvement, 15, 9, 11, and then ultimately 4, which will go ahead and go straight to our blue color. And we're going to go ahead and swap again. So 4 and 6 will swap. Swapping these 2 values appends 4 to the end of the sorted partition and puts it into its final sorted position. And rinse and repeat just like we did before, growing the sorted partition and shrinking the unsorted partition. 18 is selected as our min value. And the reason we're selecting 18, in fact, I saw 1 or 2 people do this with the linear search. Setting your minimum value to some arbitrarily large value, which has an inherent problem because your arbitrarily large value might actually be smaller than all the values in your array. So if you're dealing with an array of data that you're going to process, pulling a value from the actual array itself to use as a surrogate for a min value or some other value that is representative of the actual data set is a better way to go. Okay. All right, so we find 15 is smaller than 18. We find 9 is smaller than 15. 11 does not change our state. And then 6, we find that to be smaller than all the other values in the unsorted partition. So we'll flag that as the smallest. Go ahead and do our swap again. 6 and 18 swap. And that will put 6 at the end of our sorted partition. And we now have 3 values in their final sorted location. All right, and then we'll keep on repeating until we get there. All right, we'll take 9 out, append it, take 11 out, append it, 15, then 18. All right, so we've got 2, 4, 6, 9. All right, and 9 swapped with 15. There's 6, 9's there, it's within fine. 11 is the smallest, that's swapped with 15. All right, so we have 9 where it wants to be. We have 11 where it wants to be. And we grab 15 and it stays where it is. It's now in final sort position. And at this point, we do get to stop because there's only one element left in the unsorted partition. And by definition, a 0 or 1 element array is sorted. So there's no other way 18 can go. As we've already pulled all values that were less than or equal to 18 out. All right, so finding the smallest value is a linear component. Repeating that operation for all n values. It's also linear, giving us big O n squared. So swing back to the code. Selection sort. All right, so pair for loops, just like with bubble sort. I starting at 0. All right, less than n minus 1, like I was talking about, because once we've already pulled out n minus 1, values that are smaller, the last one will be in a good spot. Set our int minimum index equal to I. All right, so we know where we're going to need to be doing things, right? Where we want to start a comparison for our search, and then where I is going to track the end of our sorted partition. All right, so we have a micro optimization here, I plus 1. We don't need to compare index the element at an index value to itself. So we can go ahead and skip over. And then we'll go to the end. And we'll just keep on looking for someone that is smaller than our present value. And we'll update our minimum index to be that. And just keep on going till the end. And then one other small micro optimization. If we don't need a swap, we don't swap. Otherwise, we just go and call a swap function. That swaps our two values. And we'll repeat until we're all the way out. This one does not have an early exit scenario. Doesn't matter if the array is already sorted. The algorithm has no way to figure that out. So it does have to go the full run every single time. All right, so n squared is how this party is going to shake out every time. Any questions about selection sort? All right. Swinging back, we have insertion sort. It's 2.1 C. So I didn't label these correctly. B, C, all right. And the name is always helpful. Insertion sort. Oh, let me grab links. Probably already have these links in the other reading, but it makes it easier to find things sometimes. All right, so our algorithm. We're going to do something similar here and logically divide the array into a sorted and unsorted partition. Initially, the first value will become the sorted partition. Right, because remember, one element arrays are sorted. Remaining elements become the unsorted partition. We're going to go ahead and do this repeatedly. Grab the first element. From the unsorted partition. And then insert that into its sorted position in the sorted partition by shifting values to make a whole for the value we're trying to insert. All right, so that insert operation is why we call this insertion sort. All right, let me grab some color here. So starting point, I have to change things up because there's no actual swapping in this one. And let's grab some data, shall we? Good, copied over nicely. All right. So we'll go ahead and here call this, so this being a final sorted position, we'll just call it a sorted position. So 15 is our sorted array. And then go ahead, let's see what colors we want to keep here. Green for shifted and orange for selected value. And that's probably good enough for colors. All right, so we're going to go ahead and select 6 to be the value that we want to shift over into the sorted array. So as a 6 will move over, and 15 shifts. Okay, say that again. 15 shifts over, creating a hole. Over here. And then 6 sees that it's hit the beginning of the array. So we can go ahead and just drop that at the beginning. And it's now in the sorted partition, right? So we have 6 and 15 are sorted. Repeat the process, grabbing the first value from the unsorted partition. So grab 18, compare that to 15. See that 15 does not need to shift over. So we're done, and it's now part of the sorted array. Next up is 2. All right, 2 being the extreme value means we have a long way to go. All right, so we're going to go ahead and start shifting over. All right, let's just leave this blank. 18 shifts over on top of 2. I see a question. Why not a swap? Because shifting is going to be more efficient. That would, out of the 6 at pos 2. I'm sorry, Arthur, I'm not following your question. Position. Quit. Yeah, say 6 gets there, but first we made a hole. All right, so let me just point that out. Empty spots. The hole that we're creating. Right, we'll get into the details of how the shift is going to mechanically work in the code, which is copying a value into the temp and then moving things along. So 15 moves over because 2, right, is the value that we're trying to insert. So we're trying to create a hole to see if 2 fits in here. So 2 we saw was greater than 18. So we say, all right, how about to the left of 18? So 18 moves over and says, nope, 15 is to the left of, would be to the left of 2. So we don't like that as the hole for where we're going to insert into. So we'll move 15 over, create a new hole, and say, all right, do we like this hole? To go ahead and apply the value. And we don't. So we'll go ahead and keep shifting that hole over to the left till we get the hole to where it needs to be. Or we hit the beginning of the array and there's nowhere else to go. In which case we'll go ahead and drop in the value that we selected for insertion. In fact, let me rephrase this to be the first value unsorted. Once we got that where we want it to be, keep on repeating. Next up, we have 9 to get that into sorted position. Compare 9 to 18. And 18 is not less than 9. So the hole is created by shifting values over. $15 will do the same thing. Shifts over and creates a hole. This hole works for 9 because 6 is to its left. So we can go ahead and drop 9 into the hole. And next up we have 11. We'll repeat the process. All right, 18 will go ahead and make its way over. 15 will do the same. And we have shifted values such that we have a hole for where 11 will fit into the sorted array. And then one more time for 4, which has a long way to go since it is quite small. All right, and we'll just go ahead and shortcut this one. Create the hole where it needs to be and drop the value in. Yes, June. The question is, since the unsorted number isn't around while we're shifting, are we holding that value in a temp? And yes, we are. That value will be held in a temp. That's what allows us to do the shifting. Just like sorting requires a temp variable, shifting will also require a temp variable. By shifting the values, it allows us, like for example here, when we start shifting 18s, the whole is actually the previous state of the value that we copied out. Right, so we copied 18 on top of 4, so we have 18 and 18 here twice. So this old 18, we're calling a whole because state is no longer important because we've already pulled that out. And that whole just goes ahead and shifts down. All right, so grabbing the value to sort is constant time. Shifting the value into place is linear time. Again, we're talking about big O notation. So this is worst case. Worst case scenario for this sort is a descending list, which means every value we grab has to shift all the way to the beginning. All right, so if we're grabbing values like that, there's a lot of work to be done here. And repeating this for n values. It's also linear, giving us big O of n squared, just like our other two sorts. All right, now we've got the code. All right, our insertion sort. All right, key is our temp variable. All right, so we've got our micro optimization here. We can go ahead and skip the first element because that first element is our sorted partition. I'll get back to your question in a second, Arthur, after we go over the code. All right, so pretty standard for loop, starting at the beginning, going to the end. We'll grab the key that we're trying to put into sorted position. All right, so the first value of the unsorted array. And then we'll start off I, be one less. Make sure we don't run off the beginning of the array. All right, so we're going to stop looping once we get to the beginning. Or we'll stop looping once we've found where it needs to go. All right, and so where it needs to go might be already exactly where it is. We had that one time with 18. All right. Not 18, who was it? Yeah, there was 18, so long ago. We grabbed 18 and compared it to 15, said, all right, you're good. Done. Didn't have to shift anybody around. Otherwise, we start shifting. Take the value on the right and replace it with the value on the left. And we keep on doing that. I keep sliding the values over, shifting the values over to the right until we found where the hole should be, or we hit the beginning of the array. Whichever case, we'll go ahead and drop that value into the hole. Right, so if we didn't do shifting, we could do swapping, but swapping is mechanically more expensive. Thus, they're using a shift. Does that cover your question, Arthur? Right, shifting is more efficient. It's one statement instead of 3. All right, effectively it is 3 overall, right? Because we're copying a value and then copying a value and then replacing a value. So it's using the same components of a swap, but it broke it out to a singleton actions and then repeating just the second line of the swap. Any other questions about our insertion sort? Okay. Let's go ahead and take a 5-minute break. Let's break till 5 after. Gonna go ahead and go on mute. All right. Next sort algorithm is quicksort. This one is markedly more complex than these others. So take a little bit more time to get through. It is the sort that many library sort functions will use. So it is a good one to understand. In fact, if you're familiar with C++ standard library or C standard library, the sort's called qsort, where that Q stands for quick. And the reason why it's called quick is it has the best average case. Oh no, the best average case big O notation. However, its O notation is actually still n squared. And let's go ahead and go over our algorithm. That's what we're going to be doing, is choosing one of the values from the array and indicating that value to be the pivot value. Pivot value is used to group all those values that are less than or equal to the pivot to the left partition, and the remaining values to the right partition. After all values have been grouped, we'll swap the pivot in between the two partitions, which will be the pivot's final sorted position. Pivot selection. There are three common approaches. First, to just take the first value of the array. Second approach is to take middle value from the array. And lastly, median of 3, which is the median value, the first, last, and middle elements. All right, so in our example, using the first value as a pivot. And let's go ahead and grab the data. All right. So state 1, 15 is our pivot. So go ahead and let's see. Let's call that one orange. Left side, we'll go ahead and have that be blue. Right side, we'll go ahead and have that be green. No, we need to swap. So right side Come back to the second. Swapped green. And then final sort of position. We're doing teal for that one, right? So I guess right will be red. Right. Okay, so our pivot value 15. It's not exactly a great pivot, but all the values that are less to it, we're going to want to go ahead and be on the left-hand side, and all the values that we want to be on the right of it will be on the right-hand side. So I'm going to leave the right uncolored at the moment. What we're going to do is just iterate down the left-hand side until we find someone that's out of position. I guess we can color that too as well. Out of position. What colors have we? All right, pink. Let's see if that works. That looks readable. Right, 18 does not belong in the left partition. So what we're going to go ahead and do is jump over to the right and then look for values that don't belong in the right partition. All right, so the first value that we find over here on the right-hand side at the very end of the array is 4, and 4 is not greater than our pivot 15. So we go ahead and indicate that that is out of position. And we'll go ahead and do is swap that with the value from the left set that's also out of position. So we can get people where we want them to be. So we swap the two values. We're going to keep on repeating this process until the two sets have the correct data. All right, so 4 is now in the left set where we want it to be. And 18 is in the right set where we want it to be. All right, so now we look at 2. See the 2 is good. Look at 9. 9 is also good. And then 11, also good. And we've gotten to our crossover point where we have our two sets. So we have all the values, 6, 2, 6, 4, 2, 9, and 11, all less than our pivot 15. And then 18, all of our values greater than 15, which happens to be 1, might be 0. Either set could possibly be empty. So what we're going to do is we're going to swap the pivot in between the two sets by putting the pivot at the end of the left partition. Yeah, I guess we call that to show the swap first, then we can do indication of it being sorted. All right, 15 is now in its final sorted position. And we'll go ahead and remove the colors from our two partitions. All right, so now we're going to repeat this process. All right, so I'll go ahead and put a middle step here. I'm going to repeat this process on each partition. All right. So I'm going to go ahead and leave these two blank. Let's go ahead and it didn't quite work out. Let's try it again. All right, so we're now over to state 8, and we're going to select first value as our pivot. And we're working on this part of the array. We want to find values less than to go to the left set, values that are greater than to go to the right set. As it stands, all these values are less than the pivot. So we didn't have much to do. All right, this pivot selection was quite poor this go around, which is why we do have the other ways of choosing pivots. But we do now have 11 into its sorted position after we swap it. And we get to repeat the process. Whoa. That was strange. Is swapping mechanically draining when compared to shifting? His swapping is a little bit heavier to do than shifting, but we don't have shifting as an option in this case. All right, so get to now do a repeat again on this partition. And again, we have a bad, it's going to be bad partitioning all the way through here because of this nice descending sort. So we go ahead and, yeah, we'll keep it the same. But we're going to repeat. The first value is the pivot. See, all these values are less than the pivot, and then the pivot swaps. And we have it into its final sorted position. Getting closer every time we go through. And with recursion, this still has a way to go. And we'll keep on selecting pivots, finding values that are in the wrong partition, and moving things as they go. This particular example of quicksort doing quite poorly. The idea to get our better is of actually, I need to do this one differently because I got my small value there. These need to be red. Found all these values to be greater than the pivot. And then the pivot effectively just swaps with itself. Since it is itself, we don't need to swap. But we've got it into its sorted position. And recursion is taking us along the way here. We have 6 and 4 that need to be processed on this pass, and we find things out of place. Got my colors incorrect again. Fix the colors. All right, so 4 and 6 got swapped. Putting the partition, rather the pivot, into sorted position. And we're down to a pair of 1-element arrays. that need to be sorted. And by the time you get down to single element arrays, there's no work to be done. So when we get to 4, say it's one element, so we don't need to do anything. And we get down to 18, one element, we don't need to do anything. And we finally got there. All right, so selecting the pivot. Say constant time. Operation. Dividing. Sub array into left and right partitions is linear time. In the worst case. And then recursively calling. If I can type. Going to get the partitions set up. Can be linear time as well. Right, so depending on our pivots, which is why we have different ways of selecting the pivot, these divides may not be well suited for what we're doing, right? For example, if this array was already sorted, grabbing the first value guarantees terrible pivot selection because all we would be doing, right, if we have 0, 1, let's say this was our data, 0 through 6. Okay, we've got 0, down that all these are greater than 0, so 0 is where it needs to be. And then 1, same story. So it becomes quite an expensive way to validate that the array is actually sorted because we grabbed and then looped on all the values, grabbed the next value, looped on all the remaining values, grabbed, looped, grab loop, grab loop, grab loop. So we have a bunch of loops on n selections. The way that this grows towards n log n on the average case is by having the sets being halved in size, which means we have smaller and smaller sets of work to do as we do things. Okay, let's go find the code. All right, quick sort. All right, so here's our quick sort function. As the parameters, it takes the array and then 2 additional values beginning and end to represent the area of the array that we're operating on. All right, so quick sort, we get down here at the bottom. This is a recursive function. If there is work to be done on the left partition, we'll call quick sort. If there's work to be done on the right partition, we'll call quick sort again. Okay. So set up some boundaries for where partitions are going to be. This particular implementation is selecting the pivot to be the middle element. All right, so we take the beginning and the end of the array, divide that by 2, whatever value is at that position, we'll use that one. So if we do have a sorted or partially sorted array, the value that we're grabbing is going to be pretty good as a median value, bigger than about half and smaller than about half of the values in the array. micro optimization here by setting the pivot into a local variable. So we don't have to keep on indexing into the array. Our outer loop here, this is going to keep us working until we have the left partition and the right partition determined. After we have those determined, then we can get to that swap step of moving the pivot into its sorted position. Otherwise, we'll work on the left-hand side. Keep on growing the left side partition as long as the values are good. Once we find someone that's out of position, jump to the right side. Second. Sorry, my throat's a little bit damaged from my illness. Once we find someone that is out of position for the right-hand side, we can stop the loop, right? And alternatively, we do a little crossover. If we found someone that's out of position, the left-hand side being less than the right-hand side, go ahead and swap those two. And if we didn't, we'll just make a little correction here to get the proper end of the array for the left-hand side partition. But otherwise, until we've found the crossover, keep looking for values on the left-hand side that are out of position and looking for a value that's out of position on the right-hand side, and swap as often as needed. Once the partition is set, we can go ahead and swap the pivot position, and which was at the right at the beginning, and the right at the right, which will be the boundary between our two pivots. Yes, the rightmost value of the left, which because since we can find in one of two ways, because the right decremented to that position, right? Because when we come back over here, so what would happen if I can get my, where are we? All right. Right, so as we're, yes, okay, so yeah, let's go here. So when 18, when we were building this right position, we got to 18, so I was good. And then we moved over, found someone that was out of position, and then it went ahead and does the swapping. And as things go over here, the right and left are both growing towards each other. And that gets us to where we need to be. All right, and then we get to our recursive calls. All right, so our base case, there's actually two base cases in this recursive. And we get to the point where there's nothing left to sort, and then we'll stop making the calls. You want to stare at this one for a while. It's definitely hardest to visualize. Of the four sorts that we've talked about so far, there's quite a bit going on here. Okay. Our next sort is merge sort. It has a similar pattern to quicksort. We're going to go ahead and recursively divide. The array into two partitions until each partition is down to 0 or 1 element in length, meaning that they are sorted. Then we'll merge the sorted partitions back together. All right. All right, so we'll use zero-based indexing. 0 plus 6 divided by 2 is 3. So the first partition is going to be the first 4 elements. We'll do it again. So plus 3 divided by 2 is 1. Right? Integer math means throw away the remainder. Until we get down to a 1 element partition. All right, so we have one sorted partition here. Then we'll go back up, recursion, and split the right half. All right, so we're splitting 0 and 1 into 2 halves. 15 ends up being one sorted partition rather, and 6 is one sorted partition. And we can go ahead and merge those together. Looking at the front of each partition, and then grabbing from them until we have a larger sorted partition rather. Then recursion takes us back up to where we had 18 and 2 that needed to be split up. So we can split up 18 by itself and split up 2 by itself, and then those two can be merged together, giving us 2 and 18. All right, so we now have 2 and 18 merged together. So we can grab from 6 and 15. Just go ahead and start adding some colors here. All right, so this is let's go ahead and say that's a left partition, and red is a right partition. Right, and that's sorted. I guess let's go with green. Let's change that. What am I doing for sorted? Teal sorted, right? So let's not do this teal. Let's do this blue. Okay, so this is our left. And our right. Okay, it's like right here. Get my colors correct. All right, so we can go ahead and merge these two together. So what we're gonna do is we're gonna look at the first element of each, the left and right. Got 6 versus 2, so we grab 2. Now we have 18 versus 6, 6, 15 versus 18, and 18 versus no one. And we've got our left set sorted. And pop back up to 9, 11, and 4, which needs to be split. Gives us 9 and 11. Which gives us 9. And 11 by themselves. So we'll have 9 as our left partition to merge. And 11 as our right partition to merge. And then those get merged together. Brings us down to a 4 partition, which is good to go. And we'll merge these two ones together, 9 and 11 with 4. 4 will be the right set to merge. 9, 11, the left set, grabbing the front of the 2. And 9, and then 11. And then we'll have these two sets to merge together. Just comparing the smaller of the 2. So 2 versus 4, we take 2. 4 versus 6, we take 4. 9 versus 6, 9 versus 15, 11 versus 15. And then 15 versus nothing, and then 18. Okay. Any quick questions about merge sort? I've found a wall and I'm hit it. So I'm going to have to cut things short right now. What I'm going to do is I'm going to release the test answers. And we'll use Discord for questions and answers about the test questions. So just grab a screenshot, drop it in Discord, and we'll get back to it. You can go take a nap now, and maybe I'll try to see if I can get to some answers later tonight. And I'll post some more readings for where we're moving to along next. Got a few more things.
Thank you, Professor. Feel better.
Thanks. Good night.
Good night.
Make sure to take a nice nap, Professor. You deserve it.